Okay, so we have in the past few hours been looking at dimension reduction, we've been looking at cluster analysis, and now we finally come to probably the most classical topic in machine learning, namely classification. And in this today, we will look at methods, a really classical method, k-nearest neighbor, then some methods that actually perform pretty good, decision trees, random forest. They perform very good if you have limited training data. However, there's not really very satisfactory theory associated with at least the latter. So people have tried very hard to characterize random forests theoretically and have succeeded to some extent. But they are important methods in the real world. So this is what we will look at today. And then next week, we will look at methods for which the theory is very well developed, but that do not perform as well in practice. Okay? So we have this trade-off between how beautiful or how complete is a theory and how well do they actually work in practice. And a more drastic example of that are neural networks, which I would argue are still very poorly understood. And given enough training data, those are the best performing tools in our toolbox these days.
Sorry?
Yes?
Can you speak a little bit louder?
Is this louder now? Does this button do anything? Not really. I cranked it all the way up. Okay, I'll try and hold it closer. Good. All right. So we start with k-nearest neighbors as a classification method. But first, let us remind what is classification in the first place. In the first hour, I gave, as an example, this paper where scientists have taken a few seconds worth of an electrocardiogram tracing and then trained a machine to say which of a number of clinical outcomes were present in that patient, and they do just great. So they've used really a very standard method. They've used a huge training set, and they're better than the average cardiologist. So that's where you would like to go with classification, and we'll now say that in a bit more abstract terms. So classification, what we are given in the most simple setting is a training set. Xi, Yi, where the Xi have a number of names. You can call them features, or you can call them explanatory variables, or you can call them attributes, or you can call them independent variables. And these can be categorized. We have this categorization is, some people debate it, but it seems to be broadly useful. So these features could be on the nominal scale, where nominal describes a set membership. For example, a thing has ears, or a thing has wings, etc. If we want to classify, let's say, a biological organism. Or we can have the ordinal scale. Ordinal scale allows ordering of things. For example, these can be qualitative things. We can ask people, how did you like this glass of red wine? It was better or worse, or this water, how does it feel? For example, cold and warm, and we know that warm somehow is above cold, but we don't really know by how much. If we want to know by how much, then we need measurements on the interval scale. If we have features given on the interval scale, we can measure differences. Allows measuring differences. And in this temperature example, this would be numbers on the centigrade scale. And finally, we have the ratio scale, which also allows measuring differences, but in addition has a notion of an absolute zero. So this is like the interval scale, but with an absolute or with a meaningful zero. For example, in the temperature example, the Kelvin scale. So we can really say that something is twice as far from the absolute zero than something else. Okay, so our attributes can be on any of these scales. And then I mentioned that the training set consists of pairs of examples of this xi and of this yi. And this yi is sometimes called labels, or it's sometimes called targets or outputs. And this is just the most simple case. So for example, sometimes we want to predict multiple outputs at the same time, or sometimes we have incomplete data. We might be missing some of the yi's. Then we might be interested in things like semi-supervised learning. So there are many other and more advanced scenarios. I mentioned also already that we might want to predict structured quantities. But this is the most basic and the most important case of classification. So in this ECG example I gave you, the X in the training set would be electrocardiogram traces a few seconds long, and this Y's would be one hot indicator vectors telling you out of 12 possible conditions which condition was associated with that particular electrocardiogram trace. All right. Now, the first method that I want to introduce for classification is the one nearest neighbor classifier. And in a sense, this title or the name of the method already practically tells you all there is to know about it. Yes?
I have a question about the features. Do you have to convert them to each other, like maybe using a regression or classification analysis to some kind of quick processing engineering, or some regressions just handles them by its functional scale?
Okay. The question was, do we need to transform the features? And I think this will be now an interesting example answering that question of yours. Okay. The example I want to give is, I have some data set. Here I pretend that I've measured two features, and This figure, by the way, is available in this, OneNote file that you have. And I've here colored them. Yeah? So the Y I have encoded in the color. The position in this diagram tells me what are the measured features. And from this training set of a few examples, I now want to somehow, extract rules that will allow me to make valid predictions in the future. Yeah, so I said in classification what's given. I did not say what's wanted. Wanted are accurate predictions of some label given some measurement or some feature X. Okay, now what the one nearest neighbor classifier does is, let's say for a point like this one here, it simply asks which is the nearest neighbor from my training set. Well, the nearest neighbor in this case would be orange, and hence my prediction for this particular point would be orange. And let's say for that point here, the nearest neighbor for that point, the nearest neighbor will be purple, so my prediction is going to be purple, etc. And now this is where your question matters, because perhaps my feature 1 is measured, let's say this is length, and I could measure this in units of meters, and perhaps my feature 2 is a temperature, and I could measure it in terms of Kelvin. But the length, instead of meters, I could also have used kilometers, or I could have used nanometers or micrometers or whatever. And by changing the scale, of course, I will distort my points in this picture by a factor of 1,000 or 1,000,000. And when I've now said nearest, I have appealed to your intuition of, we live in Euclidean space, so normally we measure distances in terms of Euclidean distance. And there you make a very valid point that if I now change my unit of measurement, then I will distort these axes, and I need to somehow have, at least when I use Euclidean distance, I need to have some meaningful distance here. Now there are various ways to deal with it. One would be to say, okay, I normalize my data such that I have unit variance along each dimension, or we could treat this as a hyperparameter and optimize it, and we will see how to optimize such hyperparameters later today. Yeah? All right. Now, it would be nice to draw a decision boundary for these points, or I would like to somehow express, what is the rule that I learned from this training set. So what I can do is I can find those regions which have, so the set of points which have the same nearest neighbor. So for example, if we consider this point here, I'm now delineating it from the other points. So I would say broadly, or approximately this region here is the set of points for which that purple point that I had circled is the nearest neighbor. And similarly, I can do it for this point. I find a region for which that point is the nearest neighbor, etc. And if I do that for all points, I obtain something which is called a Voroni diagram. These regions are always convex, and I can now, encode the rule that I have learned. Learning here is a big word. I can encode it in two ways. One is I could say that, I color each of these Voronoi regions according to the color of, or according to the label of the point that is associated with that region. So as I, do here, so I could label these regions one by one. But if I wanted to do that in a multidimensional space, you can see that I would need quite a bit of storage, to do that. Alternatively, I can draw the decision boundary. So I can only highlight where the two classes or where my prediction changes. So the thing that I've now sketched here in black is called the decision boundary. And actually in k-nearest neighbors, this decision boundary, it's a conceptual thing. It's never actually computed. The actual computation proceeds, as the name implies, given a query. We just look for which is the nearest neighbor, and then we make a prediction based on the label of that nearest neighbor. So the decision boundary is only implicit. We can make a few observations here. For example, this point here, it is not needed to define the decision boundary. So we could eliminate it from the training set without changing our classifier at all. And there are so-called condensing algorithms that try and capitalize on this redundancy in the data. However, there's a bit of bad news, namely, if we use the one nearest neighbor classifier, then, and as we go to higher dimensions, then practically all observations contribute to the decision boundary. One can still use condensing algorithms that then try to somehow, smooth out outliers. So for example, we have here a single point that has given rise to this island. This point here has created this island. Would you believe that there truly is this island? I mean, this is a small training set which was sampled from an underlying, distribution. We have here a training set of a dozen points or so. Do we truly believe that there is such an island in the perfect classifier? Yeah?
I would say you can't tell because the sample is too limited.
Yeah, you're right, you can't tell because the sample is too small. And by the way, when I allude to perfect classifier, we will see next week what is the perfect classifier. There is a mathematical definition of what is the perfect classifier. Unfortunately, it's not a practical one because it relies on knowledge of the exact density, which we don't have. We only have the small sample. But still, it's good to understand what would be the perfect classifier. So you're completely right, we can't tell. One nearest neighbor classifier. How it works is that for each query, we predict the class membership based on the label of the nearest neighbor. And as you pointed out, beware that axis scaling doesn't matter here. Now, one can show both empirically and theoretically that this classifier has low bias and high variance. What does that mean? As you pointed out, this is a very small training set, and if I get a new training set from the same underlying distribution, I will get a new classifier. But if I average over all these classifiers, then in expectation, I will actually get a very good decision boundary out. However, as I look at the individual classifiers that I find, as I go from one training set to the next training set sampled from the same distribution, those decision boundaries will look very different. This is what is called high variance. In terms of computation, this is a lazy strategy. We have zero compute at train time. You know, effectively, there is no training. Yeah? We're just storing our training data. And then for n points, we have an O of n effort for each prediction. So it's cheap at train time. It's relatively expensive at test time. Good. Now, perhaps you have an idea how we can make the method less susceptible to creating small islands like this one here. Yeah?
We could take the distance to all points and weight them according to the distance.
Yes, we could consider not just one point, but consider more points and weigh them. And if you say that, then what you really propose is doing a density estimate, let's say a density estimate for the orange class and density estimate for the purple class, and then looking at the relative strength of those two density estimates. Yeah, and that is a valid proposal. Your answer is completely correct. Yeah, there is one method which is a little more closely related to the one nearest neighbor classifier. Yes.
Just say, for example, k nearest neighbor.
Yes, take k nearest neighbors, exactly. Yeah. So the generalization from one nearest neighbor classifier is to take the k nearest neighbors. So if we want to address this issue here of having high variance, to reduce variance, can take the k nearest neighbors. Typically, k will be an odd number, because if we do k equals 2, and we find one orange and one purple, then we still don't really know what to do. So it's typical to take k being 1, 3, 5, etc. And this helps reduce variance. What is the disadvantage of this? As we make k very large, yeah?
If it's too large, it has a higher bias.
Exactly.
Is it flexible enough?
Yeah, we start smoothing too much. Yeah. So the price we pay is that for large k, we incur a larger bias. Good, and I have another set of pictures, I hope, yes. Delete some white space here. So here, in this example, I have two data sets sampled from the same underlying distribution. On the left, this is training set 1, and on the right, there is data set 2. And in the top row, as you can see, I've done a 1 nearest neighbor classification. In the bottom row, I have computed a 41 nearest neighbor classifier. And let's look at these in a little more detail. So this is 1 nearest neighbor, 1 nearest neighbor, and we find that yeah, we have these islands, and they find different islands in the 2 different training sets. But I promise you, or I know because I've played creator here, and I've generated these 2 training sets from the very same underlying distribution. So ideally, we would like to get the identical classifier out left and right, but we don't. So this is a manifestation of high variance. What I cannot show you here is that these were now 2 training sets and 2 classifiers. If I had generated 1,000 training sets and 1,000 classifiers, and if I had averaged over them to find, on average, where do they put the decision boundary, this decision boundary would have been just in the right place. Now, going to 41 nearest neighbor classifier, these tiny islands have disappeared, and they sort of agree in the high density region, but not perfectly. So we get a broad agreement in the area where we have rather many training points. But here you see on the right-hand side where the density of training points gets very low, also the predictions start being quite different, even though 41 is a pretty large number for this small size of training set. So we will see next week methods which make even stronger assumptions and that would give you more similar results as we go from one training set to the next. Yeah? Overall, these methods, KNN, or K nearest neighbor for short, is a non-parametric method. And I'm mentioning this here because it's a very bad name in a sense. Okay, with apologies to Manuel, who is a mathematician. The statisticians, they have developed their own language, of course. And I just mentioned methods that make stronger assumptions. So for example, I could say, okay, let's do something like linear regression between the red and the blue class, and such a model, like a linear regression or something similar to it for the classification case, it has a fixed number of parameters. And if I keep the dimensionality, so I keep everything, but I just sample more training data from my underlying distribution, the number of parameters will not increase. And this type of method, which I'm just describing in words, is called a parametric method. Now here, with k-nearest neighbor classification, the complexity of the classifier increases with the size of the training set. Because the classifier, in a sense, is just the training set. So if I make it twice as large, then I am, in some sense, increasing the complexity of it. It's difficult to say, it's really a factor of 2. But in any case, as we make the training set larger and larger, the effective degrees of freedom of my method, or the implicit number of parameters, increases. So a good name, I think, for k-nearest neighbor would have been a hyperparametric method or a gigaparametric method, so something that indicates that actually this has very many parameters as we make the training set very large. But statisticians have decided to call it non-parametric. Okay? So I'm just mentioning it here because I think it can be a little bit confusing. Why is this non-parametric? So non-parametric methods are the ones that implicitly have the largest number of parameters for big training sets. Good. Do you have any questions? Yes?
So when you look at these data sets, is there a measure of homogeneity or homogeneity? So how, I don't know, how ordered my samples are basically?
So you ask, is there a measure of homogeneity? And I have not understood what you mean by that.
So if I would have basically two clouds of plots that are perfectly separated,
yes,
and so one day and the second day So they would be way more, let's say, ordered than a set which basically is completely diffused.
Yes. Okay, very good question. Does this algorithm naively tell us something about how well separated are my data going to be? Yeah? So if we look at those examples here, fundamentally you see there's overlap between the blue and the red class. So fundamentally, even the best classifier in the world, which we'll discuss next week, even if we did know the true densities, which is as much as we can ever hope for, we would not be able to get a classifier that makes 0 prediction errors. Now, the one nearest neighbor classifier always fits the data perfectly. So the one nearest neighbor classifier always thinks it's right. And it has no inbuilt measure of what is its average error going to be. If we take a k-nearest neighbor classifier, then we can invent such schemes. So we could say that, I take the 41 nearest neighbors, and then I count among the 41 nearest neighbors how many blue and how many red. And if this is a number that's nowhere close to 0 or 100%, then we already know, inbuilt into the method that there seems to be substantial overlap between the classes, and I'm not going to be perfect here. Yeah? The other possibility to do this is by means of cross-validation, which we will discuss right after the break. So, excellent question. Another question, yes?
Couldn't we just save the decision border that we calculate, and that way we don't have the problem that we always have to save it, and it gets way more complicated?
Yeah. So saving the decision boundary, the question is if saving the decision boundary is going to be a more efficient computational strategy. And it is not, because finding Voronoi diagrams, nobody works in 2 dimensions, right? So usually in real problems we have hundreds or thousands of attributes. And we have 2 problems here. One is that computing the Voronoi diagram in high dimensions is very costly. So the cost goes up with some large polynomial of the dimensionality. And the other problem I mentioned in passing is that there is something called the Delaunay triangulation. This is the dual of the Voronoi diagram. So whenever we have in the Voronoi diagram, whenever we have a face, we can say that the 2 nodes which are adjacent to, or which belong to this face, that they are connected by an edge. For example, here, these are connected. This face also connects these points. And now I can go on, and this is the Delaunay triangulation. And one aspect of the curse of dimensionality is that as we embed our finite number of training points in higher and higher dimensionality, this Delaunay triangulation becomes an almost complete graph. So here, it is actually, if I continue this, it is actually a nice triangulation, and it's pretty to look at and all. And not everybody is a neighbor of everybody. But if I add, and I've done this, but I haven't brought the pictures here, if I add just a little bit of noise, I create a third feature, which is just a noise feature, and I create just, on this scale here, a tiny little bit of noise along the third dimension, then already most points will become neighbors of most points. And hence, it's never going to be efficient to try and store explicitly this decision boundary. More questions? Yeah.
We have now only done that for 2 possible outputs, and especially choosing k already hints at that, but I suppose it's also possible to more possible.
Yes. As you say, this method generalizes to more than 2 classes. Yeah?
I'm not sure if I fully understood the method, so let's take this example. Now one goes to the 2 nearest neighbor classification. It's just possible to form islands if 2 points of the same color are next to each other. Is this correct?
Let's talk about 3 neighbors. Yeah. then yes, if there are, if we do 3 nearest neighbor classification, if we have a region where there are 2 purple and 1 orange, or 3 purple nearest neighbors, then this will be purple. Yeah? I'm grateful for the question actually, because I think I put another picture in the public document here. I've mentioned this Voroni diagram, and the Voroni diagram can be generalized to higher orders. So here, this is taken from this paper. We have the 5 points that you see, circled. They're numbered here, 1, 2, 3, 4, 5. And what you see on the left-hand side, the colors are arbitrary, but what you see is a Voroni diagram as I've described it to you. Then there are higher order Voroni diagrams. For example, this is a second order Voroni diagram, and I've put in words what it does. It delineates in these regions the set of points for which, here if we take the left example, is turquoise, here the points 1 and 5 are the 2 nearest neighbors. And so we have for each tuple of points a region, and sometimes this region can be the empty set. And we can do now the same as we go to the right-hand side. This is a third order Voroni diagram. So the 3 nearest neighbor classifier implicitly uses this higher order Voroni diagram. But nobody would implement it this way. Okay, it's just conceptually how it relates. I'm grateful for the question because, it's a cool thing. Higher order Voroni diagram, we've had the chance to talk about it. Good. Let's take a 15-minute break, after which I will talk about cross-validation, decision trees, and random forest.